going to begin here with Chapter 2 notes, which again, Chapter 1 and 2 are kind of intermingled a little bit. So we're going to cover these all in one exam anyway, one quiz. But so I just want to pick up here with a bit of a review. So I told you that we're going to have an elements quiz. So this is some prep for that. So what you want to do now is pause the video and take a second and try to fill in the answers to these questions. Do that without using your periodic table, because that's how we're going to do this in class. Okay, so I'll give you a second. Go ahead and pause and answer the 4 questions. C, N, K, C, A. Tell me what those elements are. And then down here, tell me what the symbols are for this one and this one. Okay, so I'm going to assume that you did that. And so the answer is just to check your work. C is carbon. N is nitrogen. K is potassium. A lot of people mix up potassium and phosphorus. Phosphorus has a symbol P, so don't get those mixed up. And then Ca is calcium. You'll notice that the spelling matters on this test, so make sure you're practicing how to spell things correctly. And then for the symbol here, boron, there's many elements that start with B. There's Be, there's Br, there's tons, there's Bi. So you want to make sure to practice recognizing within our list which ones are which. So boron is B, just plain B. And I remember this because boron is boring. Okay, so get it, it's just a B by itself. And then magnesium, I don't have a fancy acronym for that one or anything, or mnemonic, but it's just Mg. Okay, so that's your opportunity to review. Again, this quiz is going to be 5 questions of each type, and so 10 points possible. Okay, so the next thing is a brief introduction. We're going to come back to this later, but we're going to briefly talk about how chemicals are shown using symbols. Okay, so this substance here is a compound because the K and I are connected to each other. So when we write them sort of together this way, sort of you can think of it like almost like a word. The potassium and the iodine are connected to each other. This is also a compound. These two compounds here can come together to react and form other things. So I know they're a compound because there are multiple elements in the same sort of space. Okay, so these are compounds. Of course, over here we have our compounds that are produced on the right hand side. These are the things that we make. These are our products. So we can label the left side as reactants. Those are the things that are reacting, kind of like your ingredients. And the right hand side is the products. Those are the things that you get out of it. Okay, so again, when we write a compound, the elements are connected to each other. They're bonded. So we write them together. Okay. That means that we can't just separate them using mechanical things like separation with a filter or something like that. We have to chemically change them to get them separated. And then these symbols, after each compound in our chemical equation, these symbols are indicating what state of matter is being used. Okay, so AQ is a very common one, and AQ means aqueous, which sounds kind of like aqua because aqueous means dissolved in water. Okay, the other states of matter are the ones that we discussed in class, right? So solid, liquid, and gas, S, L, and G. So when we do a chemical reaction, we want to indicate what state of matter everything is. It helps us to figure out what it does. Okay, and we would read this reaction as potassium iodide, aqueous, reacts with, so plus means reacts with, lead nitrate, aqueous, to produce, so this symbol here means to produce, potassium nitrate and lead iodide. Okay, so that's how we read chemical reactions. We're going to get really good at that eventually, but I just wanted to introduce the idea here. So when you have a mixture, you can separate it. If it is a mixture, either homogeneous or heterogeneous, you can physically separate it, meaning mechanical separation. So you can sort it. Okay, so we did this in lab when we separated out the charcoal and the sand using filtration. Okay, so filtration, that's this method right here. So you can do that when you have a mixture. If I have a pure substance, like a pure compound in particular, you have to use chemical separation in order to separate that. Okay, so I'm going to show you this video. Right, hopefully it's gonna work here in our stream. This video is an example of chemical separation. Okay, so I just want to go back to this image of the iron here. Oh, too far. So what we're seeing here is the chemical part is sort of dissolving and kind of reacting the water with the cereal. And then we use a mechanical separation technique, a magnet, in order to remove the iron from the slurry. A slurry is a mixture of solids and liquids. Okay, and so what this shows you is that whenever you have a cereal that says iron fortified, they literally take iron powder and throw it in there because, and it's okay, don't freak out, because your body takes that metal iron flake and dissolves it when, pretty much as soon as it hits your stomach. Metals dissolve pretty well in stomach acid. So the metal is the most available, the most bioavailable when it sort of goes into your stomach as a powder like that. So iron fortified is good. It keeps people from being anemic. So don't freak out that it's in your cereal because it's supposed to be there. Okay. So what we saw was a couple of processes. First, a mechanical separation kind of based on dissolving something. And then second, a mechanical separation based on using a magnet. Okay, so we're going to work on separation in lab this next week. It'll help you nail that down. All right, so this chapter also mentions quite a bit about laws. So it's important to understand what a scientific law is. A lot of people have the misconception that a theory becomes a law. Okay, so they think that this is the progression, that if you test a theory long enough, it will graduate and become a law. That is actually not the case. They actually have two different functions in science. Okay, so a theory is sort of an explanation for why a set of experiments, rather not why, but how a set of experiments happens. So when we say theory in science, we are trying to explain how something happened. When we say a law, we're actually trying to explain something much more difficult, which is why it happens. Okay, so gravity is a theory because it explains how things fall, how things in space are attracted to each other, all that stuff. It's never going to become a law because it doesn't explain why gravity exists. Okay, that's a much deeper question. Okay, so one of the most recent laws in scientific history that's kind of been recognized was initially thought of by Einstein in 1905, and it was the idea that you can convert matter into energy. So you've probably seen his formula before, right? E equals mc squared. So the energy is E and the matter is m. It actually stands for mass. Okay, and c is just the speed of light squared. So what he's saying here is that if you get something moving fast enough, it can become pure energy. Right? So mass can become converted to energy. Okay, and this leads us to the two different laws that are sort of supported by Einstein's idea. The law of conservation of mass says that essentially whatever atoms you start with are going to be the same atoms you end with. So basically that you can rearrange atoms, okay, but you can never destroy them or create them, really. Okay, so that has some fundamental importance to us, because when I write a chemical reaction, it means that if I start with one nitrogen, I better end up with one nitrogen. So here in this example, we start off with one potassium over here, and in the end, our products, we end up with just one potassium, right? We're not making new atoms. We can't do that. Okay. Similarly, energy is also conserved, meaning you can't create or destroy energy. Okay, so both of these are really important concepts. Make sure you fill in what the law of conservation of energy means here. Okay, so when we're doing chemistry, we're going to have to learn to tell between physical changes and chemical changes. All right, so we've already seen some physical changes in the lab. Whenever you dissolve something, so we took our different mixtures and dissolved some of them with water. If they disappear and dissolve into water, kind of like sugar into water does, then that's a phase change, right? We're going from solid to aqueous, okay? That means it's a physical change. If I have a situation where the shape of something changes, that's a physical change, okay? Because neither of these things change the chemical. When something dissolves, it's still the same chemical, it's just surrounded by water now, okay? Or like if I take water as a liquid, so that's this one here in the middle. If I take water as a liquid and freeze it, it's still water. These are both H2O, so still chemically water. All I've done is change how they're arranged, so that's a physical change. Chemical changes, on the other hand, are when you go from one substance and you make something completely different. So for example, if I take iron, which is a solid, okay, and I react it with oxygen, it's going to form rust. I gotta balance this. I gotta have 2 iron to make this work out. It's going to form rust, which is that red flaky stuff on your car. Rust is completely different than iron. Iron is magnetic. It makes a nice strong car, for example, car fender maybe. Oxygen, of course, is a gas. It's not magnetic. Well, at least not the way that we think of it normally. And when I form this product, it forms this iron oxide, which is not magnetic. So iron goes from being a magnet attracting substance to not reacting to it at all. And that's one way we can tell that these are completely different. Also, the iron is a sheet of metal. It's kind of, grayish, silvery, black color. And this is red, a red powder. So it doesn't look like a metal anymore. So that's one example of a chemical change. It's oxidation, which is also called rusting. But when things burn, you can't make them, you can't reburn them. Once it's done burning, that's it. So carbon becomes carbon dioxide and it's gone. So chemical change means that the actual chemicals are different, and therefore the properties of the substances at the end are going to be different than what you started with. All right, so I want you to take a look at this slide and write down what you think is happening. Is this a chemical change or a physical change here? So let's say we write our answer right here on Statue of Liberty. And then for the fireworks here, I want you to tell me whether it's a chemical or a physical change by writing your conclusion here. And for this one down here, what this is a statue made by an artist, okay? They made it out of crayons in the desert. And so I want you to tell me whether this is a chemical or physical change. And finally for this one, tell me whether D is chemical or physical, and especially tell me why you think that.